Hello dear friends, welcome my channels. Today's discussions black hole. So friends, we discuss this video is introductory video introductions. Let I I am talking about black holes. So at first I will discuss classical mechanics. Classical mechanics converted into Newton gravity Newton gravity and it's converted into quantum mechanics. And Newton gravity converted into general relativity and general relativity or quantum mechanics both converted into information based physics. Information based physics. This is the portions, and information based of physics converted into quantum gravity. So friends, this portion is quantized and this portion is relativity. This portion is relativity. Now we discuss another portion is loop quantum gravity. This portion loop quantum gravity plus matter. It is coming from scalar tensor theory of gravity. So scalar tensor theory of gravity. And Einstein general theory of relativity. And another is conformally flat general relativity. Flat general relativity. This two portion, conformally flat general relativity and Einstein general relativity, converted into scalar tensor theory of gravity. And classical mechanics. Classical mechanics is the Newtonian converted into Newtonian gravity. I have already told my previous diagram that Newtonian gravity produced Einstein general relativity theory, and classical mechanics produced special relativity, special theory of relativity. And special theorem of relativity produced Newtonian gravity, and classical mechanics produced quantum mechanics. And quantum mechanics produced Bohmian. Bohmian. And Bohmian produced conformally flat general relativity. And quantum mechanics also produced relativistic quantum theory. Relativistic quantum theory and relativistic quantum theory, special theory of relativity, also produced relativistic quantum theory. And relativistic quantum theory produced quantum field theory. Quantum field theory. So friends, you see that this portion is probabilistic. This portion is probabilistic. This portion is probabilistic. And this portion is geometric. This portion is geometric. So friends, I discuss that how we get loop quantum gravity plus matter, and how we get quantum field theory. Now, one questions: is gravity a thing to be quantized? Now, the number one questions. Its gravity a thing to be quantized? Like the harmonic oscillator, like the harmonic oscillator, a thing to be quantized like the harmonic oscillator, the hydrogen atom electrodynamics, or Young. Is gravity a thing to be quantized? Quantized is a particular recipe. Quantized is to be particular recipe. It's a recipe for taking a classical system, a classical theory of some kind, and to convert it into a quantum mechanical theory. It's a recipe that goes back to Dirac, and it consists of a number of steps. The first step is you take the degrees of freedom. In this case, gravitational field and the metric of space-time, and you would place it by operators, quantum mechanical operators, and you invent a thing called a Hilbert space. Replace this phase, the phase space of classical mechanics. Phase space of classical mechanics, you replace Poisson brackets by commutators Z. This is just a recipe. And finally, Hamilton's equation. Hamilton's equations of motion become the Heisenberg equation. Hamilton's equation of motion becomes Heisenberg equations of motion. The important thing here is that there is a recipe for taking a classical theory and converting it to quantum theory. You can do in other ways. There the path integral approach of Richard Feynman. What the usual goal is to construct the set of Feynman diagram that will allow you to calculate processes like, for example, the scattering of particles due to gravitational force. Gravitational forces, the scattering of light by the sun, all kinds of process that you can calculate quantum mechanically, and to some extent it works, but not so well. Once you start actually trying to use it and trying to push it to its logical conclusions, all hell breaks loose. Everything comes out infinite black holes. In infinite black holes lose information, all kinds of bad things happen that are not supposed to happen, and so I would say to some extent, perhaps the more than some extent, it being a failure. The quantizations of gravity. Maybe failure quantizations of gravity. If it is just a classical theory to apply the recipe, a contradictions between gravity and quantum mechanics. It may be too strong to say that gravity and quantum mechanics are exactly the same, but to those of us are paying attention, we may already sense that the two are inseparable, that neither makes sense without the other, and two things make me think. So I am going to describe those two things today and go into some detail, not technical detail but conceptual detail. The first of them is called ER. ER equals to EPR. I will tell you, but right now I had not intended to tell you more. I will tell you anyway. ER stands for Einstein. EI stands for Einstein-Rosen. And EPR stands for Einstein Podolsky and Rosen. I will tell you, but right now I had not intended to tell. Okay. Einstein was short of his assistants. Well, you have heard of Rosen, but Einstein was short of his assistants. Einstein and Rosen, who wrote a famous paper about gravity in 1935. 1935. EPR stands for Einstein, Podolsky and Rosen. Podolsky was another one of Einstein collaborations who wrote a famous paper about quantum mechanics. That same year, let's start with the idea of formation of black hole. Of a black hole, very simple, a cloud of particles. Formations of black hole. Formations of black hole. Very simple. Very simple, a cloud of particles indicated by a bunch of little points. A bunch of little points collapse under its own weight. Due to its own gravitations, the particles get pulled together by gravity. Own weight due to due to its own gravitations. The particle can be the particle get pulled together by gravity. And what happens to them? Eventually they form a black hole. They form a black hole. That the basic process that we will be interested in, and of course there's no reason why this should only be one black hole in the world. Two clouds of gas somewhere as in distant parts of the universe could independently collapse and form two black holes. We could call one of them Alice's black hole. I suppose that the one on the left is Bob's black hole. This is Alice's black hole, and this is Bob black hole. No interaction, no connections. There's Alice's black hole over there and just two black holes. What do they have to do each other? Not much. They were formed independently. They are uncorrelated. They are not interacting with each other. Uncorrelated. They are uncorrelated. They are not interacting with each other because they are far away from each other, and so we would say that they are statistically and dynamically and always independently of each other. No interaction, no correlations, and if perchance Alice happened to fall into her black hole, and that would be the end of her, and Bob fell into his black hole, that would be end of him and the story. This is the story. Alice fell into this black hole and Bob fell into this black hole. This is the Bob's black hole and this is called Alice's black hole. Now what I imagined now is that we formed the black or linoleum that we do. I want to talk about entanglement. EPR entanglement. EPR entangle. EPR entanglement. Entanglement is the thing that Einstein, Podolsky, and Rosen discovered what is entanglement. And entanglement between system, it could be the entanglement between two electrons. Entanglement between two electrons, it could be entanglement between two protons, it could be entanglement between any two things. Entanglement is quantum mechanical. It's quantitial quantum mechanical property. The systems can have pairs of systems that never makes any sense classically. If I were to tell you that I know everything that there is to know about a pair of systems, these two things over here, if I know everything that can be known about the composite system made out of these two things, one of these are things. If I were to tell you that I know everything, or that everything that can be known about system is known, you will say, well, must mean that everything about the parts of the system are known. How can it possibly be that you know everything that can be known about a system and not also know everything about the two parts of the system? Well, in quantum mechanics that can happen. You can know everything about a pair of electrons. This is supposed to be a pair of electron spins. The spin can be up or it can be down to electrons. And for those who know a little bit about entanglement, you will recognize this as an entangled state, in which you know nothing about the first particle. What do I mean by you know nothing about it? It could equally will be likely to be up or down. So if it's equally likely to be up or down, you know nothing. The second particle can equally will be down or up. Again, you know nothing. And yet this is as complete a description of the state of an electron of a pair of electrons as you can possibly have. What do you know? What do you know is correlations. You know that if the first electron is measured to be up, the second one is definitely down. If the first one is measured to be down, the second one is necessarily up. It's either this is on, this is this that's the character of entanglement, something that never happens classically. Quantum mechanically, two particles which are entangled in this way are usually called Bell pairs. Bell does not stand for the thing that you make a sound with John Bell. The physicist John Bell, who spoke about a great deal of this did a great deal too, but this is essentially to Einstein-Podolsky-Rosen idea, entanglement, and we usually use a little graphical notation to indicate that two particles are entangled, namely just draw a line between them and that indicates they are entangled in this funny way. Okay, now let's imagine again that we are going to create two black holes, but instead of just creating them, this is the two black holes, and this is a straight line, and this is the straight line. The particle is moving. This is the entangled particle, entanglement. Line between them, and that indicates that they are entangled in this funny way. Okay, and independently, what we are going to imagine is that we create first a bunch of Bell pairs. We create a bunch of Bell pairs. A large number of particles which are entangled with another large number of particles. This particle is entangled with this one, entangled with this one. We create them in laboratory, and then we separate them. Separating them does nothing to destroy the entanglement, and so what we wind up with is two entangled clouds of particles, and then on each side the particles collapse to form black holes. And what does that make? Well, it makes two entangled black holes. That means that if you measure something about this one, you learn something about this one. Two entangled black holes, Einstein-Podolsky-Rosen entanglement. in this case between black holes, and this is something that it's. How are they entangled black holes different than unentangled black holes? And here is where something strange happens. I am going to tell you this is the outcome of many years of research, the last 20 years research and 25 years research. We will talk a little bit about it. I'm going to tell you right now what has been learned. Now take a look at this. This is a supposed to be y space y. This is space y. Had let be bent it over like that, bending over like that. There's nothing real to it. If I have a piece of paper and that piece of paper is flat, if I bend it like that, that does not change geometry of the sheet of paper, intrinsic called the intrinsic geometry. The intrinsic is the same. Intrinsic geometry is the same whether this way, but I can make a point. I have taken space and folded it over so that this region over here is close to that region on the diagram. These two places are very far apart. If Alice wants to get the bob, she has to walk all the ways around here. Alice and Bob have created a pair of entangled black holes. The new theme, and because they are entangled, is that an Einstein-Rosen bridge forms between them, and Einstein-Rosen bridge is popularly called a wormhole. It's a route through space which short circuits the long distance between these up to my. These are the craziest things we have discovered in the last 20 years, that the existence of entanglement creates spatial connectivity between two regions which would otherwise be very, very far apart. Now, does that mean that Alice can send a signal to Bob, short-circuiting the long distance between them? No, it doesn't. Entanglement doesn't provide a way of sending messages. It's correlations, but it's not message sending. Alice cannot. When we are going to come to the reason why soon enough, why Alice can't use this wormhole, this Einstein-Rosen bridge, to send a message directly to Bob. and she cannot violate the rule that to send a signal from one place to another place, that it goes faster than the speed of light. It would be going faster than the speed of light, at least the speed of light around this direction of Alice, and could send message to Bob. There are two ways to think about the form. From the point of view of entanglement, there is a theorem. The theorem says that entanglement can never be used to send the signal from one place to another. It's correlations, but it's not signal sending. From the point of view of general relativity, from the point of view of these wormholes, it's the non-traversable and character of wormholes that you cannot cross from one to the other, from one side to other. We are going to explain why that's true. Nevertheless, the fact that Alice and Bob cannot send message through the wormhole, there is something else that the extremely odd, and this is a property of general relativity. It's a property of this Einstein-Rosen bridges, namely that Alice and Bob can decide to jump into their respective black hole and meet at the center. So let's just review. We take these entangled particles, we separate them out to the ends of this universe, we collapse them into the black holes, and then Alice jumps into her black hole and Bob jumps into his black hole, and they can meet in the center after a very short time. That is the remarkable conclusions of its true. But the only things hoops let's go back, the only thing that they are meeting at the center can never be reported to the outside. They are stuck behind the horizons of the black holes. They have jumped in there behind the horizons of the black holes, and they cannot report in the outside world that they have discovered some each other on this inside. So somebody on the outside will not experience any indication that something very strange has happened because this entangled. For experts here, the proof is Penrose diagram. So we know, friends, Penrose diagram. So let's draw a diagram of the Penrose. This is r equals to, here r equals to 0, and this is the parallel horizon, and this is horizon. This portion is horizon. This is parallel horizon, and this is horizon, and this is r equals to infinity and r equals to infinity, and this portion is universe, and this portion is white hole, where r equals to 0, and this is the black hole. Here is black hole, and this is parallel universe. This portion is parallel universe. This is the Penrose diagram. Here r equals to infinity and r equals to infinity. This is Penrose diagram. This is a picture of diagram, a mathematical diagram of the two black holes that were created very from apart, but in which you can pass from one to another through a wormhole holes. What this picture is saying what the previous picture is saying is that Bob and Alice can jump into their respective black holes and meet center, all right. So that's a mathematical proof. Did you catch the proof? No equations, but mathematical proofs that two entangled black holes and they are entangled. Two entangled black holes can be used not to send a message through. Notice you cannot not send a messages through. Notice you cannot send message from this side over here to the side over here. I would exceed the speed of light, but the two participants can jump in and meet at the center. That's a crazy thing. 25 years experience of 25 years of many physicists. It began with something called the holographic principle. Holographic principle, which I won't go into. I was involved it heavily, but okay. Holographic principle is called loops. The holographic principle is called gauge gravity. About a little more, one version of it is called matrix theorem. Matrix theory, it goes back to 1996, but most of all the most important thing that goes into this argument is called ADS CFT. I am going to tell you what that it is. It was discovered by Juan Maldacen. Name is who discovered Juan Maldacena. In 1998, and it has been the main driver of research in quantum gravity for at least the last 20 years. It has been extraordinarily fruitful. So let me tell you what it is. The holographic principle is the idea that a regional space can be described by degrees of freedom, and physics on the boundary of the region of space. That idea become extremely precise with the work of Maldacena, and here's what it says. It says it in kind of space called, this is the I draw two spaces. At first my drawing is this is ADS. This is strongly configured, large and configured and large gravity theory. Here's what it says. It says in kind of space called AIDS, stands for anti-de Sitter. AIDS is called anti-de Sitter. Anti-de Sitter space. And it was invented by de Sitter. This was the space that was invented by the sitters. Sitter space is the opposite, but this is way to think about. It's a space. Time runs up, what space runs across, and it's space that you can think it as being a fruit cavity in a finite. It is as being a finite cavity in a finite spherical box with reflecting walls, so that anything that hit the wall of the box and bounces of everything take place within this box. Time runs up, space runs across, and it's a space-time that has gravity in it. It can have black holes. It can have pupil. The pupil can fall toward the black holes, and it's called the bulk space. It's three-dimensional and d-dimensional here, but it's three-dimensional space in here. The holographic principle, or ADS-CFT, says exactly this state. The SAW system is equally described mathematically by a theory of degrees of freedom that live on the boundary of the space. Purely the boundary and those degrees of freedom constitute a quantum field theory. Quantum field theory whose degree of freedom are entirely restricted to the boundary of space. That quantum field theory has Feynman diagram and particles and so forth, but they don't move into the bulk. They live only the boundary, and while the same is discovery is that these two theories are exactly the same and it describes the same thing, that is also crazy here. The mathematics is extremely precise, and so it will. You don't have to believe any of them. This kind of gauge gravity or ADS safety duality. Quantum field theory that describes the boundary of space, or that does not describe the boundary of the scripts, everything inside the space, but it lives on the boundary. It's a field theory. On the boundary, that the kind of quantum field theory is very familiar kind of quantum field theory, but it occurs usually. You think quantum field theory is having to do with elementary particles, but the place where quantum field theory also really has had a tremendous impact in physics is in condensed matter physics. Just a lump of material, if it's quantum mechanical, and of course all the material are quantum mechanical, but described by the quantum field theories. Those quantum field theories, for example, can govern the phonons of the propagating in a crystal lattice and fluctuations of superfluid superconductions, fluctuations of Fluctuations of a super superfluid superconduction magnetic superconduction magnetic system, quantum Hall system topological insulation, and those quantum field theories are very similar to the kind of quantum field theories that go into the gauge gravity. There is no known objections or obstruction. Their engineering is strongly coupled large a gauge theory. On a shell of silicon, you would have to dope the silicon, you have to put in some extra stuff. But this, when I say silicon, that does not have to be silicon, that just a metaphor. For a piece of material are constructing a set of degree of freedom that live on a shell, that the property of behaving exactly like the kind of quantum field theory that gauge gravity duality is all about. So I want you to imagine created such a shell in a laboratory. There is a shell of matter. So Alice test a test. Alice want to test ADS or CFT. There is a shell of matter. It's a shell. It's hollow. There's nothing inside. It has been engineered in just such a way that it is described all of its properties of the describes by a quantum field theory that lives on that shell, that has just the properties of the kind of Maldacena thought about when he talked about the relation between anti-de Sitter space and the boundary quantum field theory. There it is now Alice who's the experimentalists in the laboratory. Once the check is there, in some sense an equivalence between the things that go on the shell and some kind of theory that lives in a bulk, in a hypothetical bulk. I am not going to tell you where the bulk is, but she is going to do some experiment on the shell, the first thing she does for the shell is if she taps on its tapping on it will create a excitations on it. Now from the point of view of the shell, looking at the shell, you might expect that the perturbation create waves which go around the shell and focus at opposite end. If you were a believer in the existence of a bulk, then you might say that tapping on the shell over here shoots a particle into the bulk, which propagates across to the other side. In both cases, you will find that something goes across from this end to this end in a certain amount of time. And in fact, if you calculate in the anti-de Sitter space geometry how long it takes for a signal to go through the bulk, it's exactly the same as the time that it takes to go around the boundary. So that's a chick Alice does this. She taps on it over here. She goes and looks over here and something come through the bulk and she can say something went through the no difference. She can do other kinds of experiments. In fact, she can get together with Bob Alice will tap on this end Bob bulk boundary theory. Alice believes that some kind of objects at the center of the bulk of the geometry here, and she taps on the system that creates a signal that goes into the bulk. If you believe in the bulk hits the objects over here, and if the objects is the right kind, that might start it ringing. If it was a bell, it would start it ringing. If it rang, it would send out waves. The waves were propagated out to the boundary, and by standing out near the boundary of the shell, here the shell the boundary out near the boundary, she would discover the kind waves propagated out. She would feel it. She would be able to detect these waves and hitting the boundary, and she would calculate that there was something at the center. It had some properties and they could be proved by from the boundary from her outside laboratory by tapping on the shell. So lesson to be learned here is that Alice can either think that the boundary theory created waves which went around the boundary in very complicated ways, or she can think equally well that there really is a bulk on the inside of the shell, and that stuff can propagate in heat, things scatter and be detected at the boundary now of the things that we can create in the bulk is a black hole. How do we create a black hole? I just have to tell you this, the way you create a black hole. Starting with just the shell of silicon, you heat it up. That's all, you heat it up. Just heating it up creates energy on the shell. And the dual description of the that from the point of view of this d ADS CFT holographic descriptions in that black hole is obvious, but that are one of the things that goes with the idea. This idea, how can you heat the shell? One way you can heat the shell is just illuminate it with laser until it's heated. It creates a black hole inside the bulk. Of course, you can't see behind the black hole horizon for the usual reason. Nothing can escape from the black hole, but you could do other experiments. Having created the black hole, you could heat it with something, and the something and black hole ring. Black holes do ring. Black holes, they have quasi-normal modes, which are like ringing modes. Quasi-normal modes. Normal mode. Allies could in fact attempt to discover whether there's a really black hole at the center of the shell. She would discover that there is a create two black holes some way. We create two shells. Let's start with two shells. So friends, this is the story. I will continue it in another video. But whatever we have learned that Alice Bob story, and we also learned EPR, Einstein, Podolsky, Rosen, and we learned about anti-de Sitter. So friends, we need to now learn some mathematical formulation. Bohm's variant of the EPR paradox can be expressed mathematically using the quantum mechanical formulations of spin. So EPR, now I discuss mathematical formulations. Quantum mechanical formulation of spin. For EPR, two-dimensional, the spin degree of vector and electron is associated with two-dimensional complex vector space. Two-dimensional complex vector space V with each quantum state corresponding to vector in that space. The operator corresponding to the spin along the x, y and z direction. Operator corresponding to the spin along the x, y and z directions. Denoted by Sx, Sy, Sz. It can be says Pauli matrix. Sx, where Sx is equal to h bar by 2, 0, 1, 1, 0. Sy equals to h bar by 2, 0 minus I, 0. Sz is equal to h bar by 2, 1, 0 and 0, minus 1. H bar is the reduced, H bar is called reduced Planck constant. Now, the eigenstates of Sz are represent as plus z tends to 1, 0 and minus z equivalent to 0, 1 and eigenstates of Sx, eigenstate of Sx represent plus x equivalent to 1 by root over 2 1 comma 1 comma minus x equivalent to 1 by root 2 1 comma minus 1. The vector space of the electron positions pair is V cross V. Space of the electron position pair is V cross V. The tensor product of the electrons of electron and electrons and positrons vector space. Positrons vector space. The spin singlet state is the spin singlet state is 1 by root 2 into plus z and minus z minus z we need to show that after analysis measurement of Sz or Sx for Sx and Bob's value of Sz. Bob value of Sz or Sx. This follows from the principle of measurement of quantum mechanics. This follows the measurement of quantum mechanics. So friends, thanks for watching and your kind attention. I hope I will create more video based on theoretical physics.